Time and space are flexible and stretchable, much like a fabric, and can be imagined as a trampoline net. When you shape this net like a pretzel stick, imagine it being possible to travel back in time. Have you ever questioned what the universe really is? Have you wondered how it can hide its fascinating mysteries from us? You are about to embark on a journey of discovery that will completely change what you know about the universe. Get ready to explore a groundbreaking discovery by the famous American physicist Michio Kaku. The legendary James Webb Space Telescope, which might have proven that time does not exist, is ready to take you into the complex world of space-time. The James Webb Space Telescope, launched on Christmas Day 2021, is a more advanced version of the Hubble Space Telescope. Equipped with super-powerful infrared devices, it is designed to illuminate the secrets of the darkest and most distant corners of the universe, functioning almost like a time machine. How is this possible? By providing unprecedented resolution and sensitivity, it can detect incredibly old and faint objects that even Hubble cannot see. We're talking about objects from distant galaxies in the early universe. The James Webb helps us piece together the grand puzzle of the universe filled with large stars, one infrared image at a time. Now, imagine yourself strolling through an art gallery. The breathtaking photos taken by the James Webb Space Telescope present a stunning cosmic canvas filled with images of distant galaxies shimmering. However, among astronomers and cosmologists, you feel a sense of shock and disbelief, much like the chaos one might feel looking at a Picasso in a room full of realism. The common sentiment is that this is unexpected. Although official documents provide little information on this, the core issue lies in a theory they stand on: the Big Bang hypothesis. This is the idea that our universe began with a massive explosion about 14 billion years ago. This theory has been a cornerstone of cosmological understanding for years, but the new images from JWST challenge the validity of this theory and send shockwaves through the community. You can almost hear the seasoned perspective of astronomer Alison Kirkpatrick from the University of Kansas, questioning why the galaxies captured by JWST are so astonishing. According to the Big Bang hypothesis, the behavior of these galaxies is far beyond what was expected. They are too small, too smooth, too old, and too numerous. Let's summarize two small enigmas. If we think of the universe as an expanding balloon, galaxies should appear smaller as they move away from us. However, after a certain point, they should start to appear larger because their light was emitted when they were closer. This represents a strange but important shift in the concept of an expanding universe. Yet, the images obtained from JWST show galaxies almost the same size as those near us. This is like expecting distant friends to appear as tiny dots on the horizon, only to find them standing next to you, life-sized. Interestingly, these images show galaxies smaller than expected, even those brighter and more massive than our own Milky Way. These images might show galaxies as 2 to 3 times smaller than what the Hubble Space Telescope, HST, observed, despite their greater brightness and mass. Moreover, these galaxies have significantly higher redshifts, which, in layman's terms, means they are receding from us at higher speeds. You might find this strange, and you would be right, especially if you are working under the assumption of a continuously expanding universe. In 2014, some scientists pointed out this inconsistency. They analyzed HST images and found that the redshift of galaxies matched what would be expected in a typical non-expanding space. It was expected that JWST would continue this trend and even observe this phenomenon in galaxies with redshifts up to 12. Simply put, JWST images show galaxies that appear the same size as those close to us, as if the universe were not expanding and redshift was just a function of distance. However, if we adhere to the Big Bang Theory and the concept of an expanding universe, a very confusing result emerges. These distant galaxies should be unimaginably small to balance the optical illusion created by an expanding universe. This is akin to imagining a grain of sand shining with the brightness of a spotlight. For instance, a galaxy called GZ2, which JWST found to be much brighter, has been calculated to have a radius of only 300 light-years, compared to the Milky Way's 50,000 light-year radius. Its brightness per unit area would be 600 times that of the brightest galaxy in our local universe. When we consider these small and smooth galaxies within the concept of an expanding universe, we find that some new galaxies are tens of thousands of times denser than the galaxies we see around us today, which could challenge the Big Bang Theory. These findings have generated significant excitement among astronomers and cosmologists over the years. The images from the Hubble Space Telescope revealed the existence of many dense and powerful galaxies, reminiscent of Mighty Mouse in old cartoons. These galaxies pose a challenging puzzle for them, and with the new James Webb Space Telescope, understanding these strangely small galaxies has become even more difficult. Theorists describe the situation as if they were playing with a tiny toy car. Imagine a magical car that, despite being only 1 centimeter long, weighs as much as a real SUV. They propose that these small galaxies collided with each other over billions of years, forming the full-sized galaxies we see today. It's like toy cars crashing into each other and transforming into real SUVs. However, when JWST took a closer look at these galaxies, it found no evidence of such cosmic collisions. You would expect these colliding galaxies to show some signs of damage, perhaps appearing a bit jumbled or crushed. But we see nothing of the sort. Instead, JWST reveals galaxies that are smooth spirals, just like the ones nearby. There is a significant lack of signs of galactic collisions. In fact, a study titled Panic highlights that these undisturbed spiral galaxies are 10 times more common than theorists predicted. This is like finding cars speeding on a busy highway, but with no accidents. The collision theory, with no signs of galactic mergers, takes a substantial hit. The idea that these small galaxies somehow expanded into larger counterparts suggests that if they didn't grow, they would disintegrate. This implies that they are not actually small. As a result, the optical illusion we would expect from an expanding universe does not appear here. The concept of expansion is losing ground, leading to growing unease among Big Bang enthusiasts. The existence of these small, smooth galaxies suggests that the universe might not be expanding, and if true, it would deal a significant blow to the Big Bang Theory. If these galaxies existed before the Big Bang, it would mean that the Big Bang did not occur. This could be a game changer for our understanding of the origins of the universe. Think of the James Webb Space Telescope as a time machine, in line with Michio Kaku's words. This incredible device, capturing images that reach back into the cosmos billions of years, shedding light on the origins of the universe, does not take photographs in our familiar visual spectrum. Instead, it focuses on the infrared, revealing the colors of galaxies so distant we could never observe them. The fascinating part is that these colors are not just beautiful. They tell a story about the age of the stars in these galaxies. Young, fiery stars shine in vibrant blue, while older and cooler ones glow in yellow hues. By examining the red colors, astronomers can estimate the age of the star populations in these distant galaxies according to the Big Bang Theory. The most distant galaxies in JWST's images represent a cosmic snapshot about 400 to 500 million years after the birth of the universe. However, some suggest that these galaxies appear to host stars that are billions of years old. If you follow the Big Bang Theory, you know this is a major problem because nothing can be older than the Big Bang itself. If the Big Bang Theory is valid, as we look further into space, and therefore back in time, we should see fewer and fewer galaxies until we reach the cosmic dark ages. But this seems to be a different story. It appears that galaxies as large as the Milky Way were quite common, even just a few 100 million years after the supposed Big Bang. New images show that there are at least 100,000 times more galaxies in regions with redshifts greater than 10 than predicted. Many large galaxies could not have formed in such a short time, at least under the constraints of the Big Bang theory. Thus, these discoveries challenge the very foundations of our understanding of the universe. Moreover, there's another interesting detail. Some information suggests that the Big Bang theory might be wrong in many respects. Recent research suggests that 16 predictions of the Big Bang theory are incorrect, and only one prediction is accurate. This is the abundance of deuterium, a type of hydrogen, which is correctly predicted. However, the theory predicts twice the amount of helium and 20 times the amount of lithium observed in the universe, which is incorrect. The Big Bang theory also struggles to explain the enormous structures we see in the universe, structures that are too large to have formed since the beginning of the universe. The theory also has problems estimating the density of matter in the universe. Additionally, the theory proposes that the cosmic microwave background asymmetry does not exist, which contradicts findings showing that this asymmetry does exist. It's like a cosmic plot twist. Looking at the James Webb Space Telescope, this technological marvel might hold answers to these questions. These cosmic contradictions may seem like very small details in the vast panorama of cosmic knowledge we have gathered. However, they are too important to ignore. Every small error is like a missing piece in our cosmic puzzle. The big picture leaves us with an incomplete understanding of the nature and origins of the universe. It should be noted that these anomalies are foundational to our understanding of space and matter. These findings challenge everything we thought we knew about the formation of the universe and our understanding of the evolution of the cosmos. They challenge our grasp of space-time fabric and cosmic structures, fundamentally affecting our understanding of universal expansion, gravitational waves, dark matter, and even the ultimate fate of the universe. For instance, if the density of matter is off, this could change our understanding of how galaxies form and evolve, as well as our perspective on the role of dark matter in this process. Similarly, unexpected asymmetries in the cosmic microwave background could affect our knowledge of the initial conditions and expansion rate of the universe, further exacerbating these inconsistencies. This also impacts our understanding of time itself. You see, our current understanding of time is linked to the evolution of the universe since the Big Bang. If the Big Bang theory is found to be inadequate, we may need to rethink how we perceive the flow of time and its connection to it. Consider space. These findings could lead to a paradigm shift in our understanding of space-time, similar to when Einstein introduced the theory of relativity. We might be on the brink of a new understanding of the cosmos, requiring us to recalibrate our cosmic clocks and redefine our cosmic compasses. The universe still seems to hold some surprises. Have you ever thought that time might be an illusion? Let me ask you this. Have you ever wondered if time, as we understand it, really exists, or if it is just a human construct? Time is a concept that helps us distinguish the past from the present. It's a difficult question, we know, but keep it in mind. There is a theory suggesting that time is an illusion created by our human memories. This theory posits that everything that has happened or will happen is happening right now. It sounds a bit strange, doesn't it? Let's delve a bit deeper. Naturally, you think that time flows forward, but guess what? The laws of physics require them to operate the same way, regardless of whether time moves forward or backward. You've probably heard of the Big Crunch theory. It suggests that when the universe finishes expanding and starts contracting, time could begin to flow backward, and as the universe shrinks, it would heat up. It suggests that a kind of reverse Big Bang could occur. The Big Crunch is a puzzling question for all of us. Some theories suggest that a new universe could emerge from a new Big Bang, while others propose that our universe could reappear elsewhere, like a cosmic balloon popping. There are even theories suggesting that this cycle could renew itself over and over, leading to countless universes. This strange possibility of time moving forward or backward has led some scientists to a bold conclusion about time. They argue that it is merely a human construct. They claim that we live in a block universe. Space and time are intertwined. In this scenario, it is a concept supported by Einstein's theory of relativity. All events in the past, present, and future have their own coordinates in four-dimensional space-time. What does this mean for us? It suggests that everything is as real as the present moment. The past and future still exist somewhere in space-time. MIT physicist Max Tegmark has beautifully explained this concept, noting that we can view our reality as either a three-dimensional place where things happen over time, or a four-dimensional place where nothing ever changes. If the latter is true, then time is an illusion because nothing really changes. The past, present, and future are always there. There is certainly a lot to ponder. But isn't it fascinating to think about these kinds of questions? This shows how mysterious and captivating a universe we live in. Julian Barber is also an English physicist with quite an interesting perspective on time. Our reality can be thought of as a series of different moments, much like looking at a photo album filled with separate snapshots. Barber views the universe in this way. According to him, our perception of the past is a structure of memories in our brain, meaning we feel the past exists only because we have memories of it. According to Barber, the very concept of the past could be an illusion, and he explains this concept in more detail in his theory. Each moment is located in a vast landscape he curiously calls Platonia. Every point in Platonia represents a present moment, and this landscape follows perfect mathematical rules that make it timeless. This perspective is also connected to Albert Einstein's theory of spacetime. Einstein's theory is at the core of our current understanding of the universe, but the implications and our grasp of this understanding raise some critical questions. If Einstein's concept of spacetime were flawed, could we set it aside completely? Would it provide us with a clearer understanding of the universe? The world of science evolves with such revolutions. Theories are constantly questioned, refined, and sometimes completely changed. Through this continuous cycle of inquiry and discovery, science advances. Looking back at history, we can see how this process works. The geocentric model, which considered Earth as the center of the solar system, was widely accepted for over 1,000 years. Then, Nicholas Copernicus came along with the idea that Earth is not the center of the solar system. He proposed that another planet orbits around the Sun. Following Copernicus, whose ideas eventually replaced the geocentric model, Isaac Newton presented a new understanding of gravity, proposing that all objects with mass exert a gravitational pull on each other. The Earth orbits the Sun, and the Moon orbits the Earth due to mutual gravitational attraction. Newton's theory of gravity remained in place for about 300 years. Then, in 1915, Albert Einstein introduced the theory of general relativity, redefining our understanding of gravity. Einstein proposed that massive objects cause curvature in the fabric of space-time. The Earth orbits the Sun because it follows this curvature, which is what we perceive as gravitational force. The transition from the geocentric model to the heliocentric model, and from Newton's gravity to Einstein's general relativity, highlights the evolving nature of scientific understanding. Today, physicists continue to push the boundaries of our understanding of time in the universe. Einstein's concept of spacetime has withstood all challenges for over a century. The detection of gravitational waves in 2015 marked a significant triumph. But no theory is perfect. General relativity, which includes Einstein's concept of spacetime, encounters a significant problem when faced with quantum physics. The two seem to operate under entirely different rules, and this creates some issues.